recovered from the process last night. Anyway, Happy New Year. Okay, so we continue into this deep dive into the concept of information, and I just want to reiterate some of the things I said last time, clarify them just to make sure that you understand them. So essentially, again, we define entropy, which is the measure of uncertainty, which is just the expectation of the log or minus the log of the probability distribution. So in a sense, we are thinking about this minus log p as some sort of a random variable. So it actually has a slightly different meaning than p. So this is actually the averaging quantity, and this is the observable in some sense. Although they're both made out of p, they have different conceptual meaning, and we're going to see it in many more ways. So log p has is like the uncertainty in the event that is probability is p, and or minus log p, and p is the averaging. So we're actually thinking about them as in two different ways. So it's a bit confusing, but we'll see it again and again. So this is again the entropy of x, or the entropy in the. I'm keeping only the good ones here. So it's the entropy of the probability distribution. So we think about entropy as a function of the variable, which essentially measures the uncertainty in x. And from the entropy, we define the conditional entropy. So how much uncertainty is left in x when we know another variable or know something about another variable, which was just the average over y of p of y, the entropy of x when y has a certain value. Now we know that this average is always smaller than h of x, and no matter how many times I condition or what but it doesn't mean, by the way, that every one of those elements is smaller. I mean, some of those elements can be larger or smaller than h of x. So which means that some values of y can reduce a lot of uncertainty, and some of them can actually increase the uncertainty. But on average, it's smaller. Okay? So this is a very common mistake. I mean, the fact that conditioning reduces entropy doesn't mean that the condition on the individual value of the variable y really reduces entropy. Now, from that, we define the mutual information between two variables as the entropy of the amount of uncertainty removed by the knowledge of the other variable. So it's, and as I said, I mean, because of this is a non-negative quantity, and they actually proved it because this is a DKL, because this is simply the KL divergence between the joint distribution and the product of the margins. Okay, this is why it's non-negative. And it's, of course, has similar several other expressions depending h of y minus h of y given x, and h of x plus h of y minus the joint, and so on. And from that we define, in a similar way, we define the conditional entropy and conditional information. So how much information, So this is essentially the uncertainty removed from x when I know y. And this is the uncertainty, or the uncertainty removed from y when I know x. Both of these things are, so this is greater than 0, but it's always bounded by the minimum of hx or hy. So it can't be larger than any of these. Okay? And this is unreadable. So it's greater than 0. Let me say it here. I mean, it's bounded by the minimum between age of x and the age of y. So if age of y is small, then any of them is small, then the information cannot be larger than any of them. Okay. And the conditional mutual information was defined in a completely analogous way to conditional information. So it's the removal in the conditional entropy of x when I know my y. And I just want to make it clear again, this is always, just because it's entropy minus conditional entropy, this is always non-negative, but we don't have that conditioning reduces information. So the second step, I mean, conditioning on another variable can actually increase or decrease information. So unlike entropy, that we know that this is always positive, the difference between the information and the conditional information is not necessarily positive. And this is somehow confused you. So I'll give you all the examples. Ixy minus Ixy given z, which is completely analogous to this. I mean, the entropy, the uncertainty in x minus the conditional uncertainty in x. This is the conditional the information minus the conditional information in x. When we talk about three variables, this is not necessarily positive. It can be both positive and negative. That's what confused me last time, and I just want to make sure that you are not confused because of it. And this is something. This actually the minus of it is something we call synergy. Synergy of x, y, and z. And this is actually surprisingly a symmetric quantity. I mean, it doesn't any permutation of x, y, and z will give you the same value. So this is the same as Ixz minus Ixz condition on y, or Zy minus Izy condition on x, and so on. Actually, what 6 permutations if you want? Yes.
Can you give an example where the condition on z and it becomes?
Yes, I know. You asked your questions 3 times already, and I'm going to give you an example. It's all right. Okay, just a second. Okay, so this is, again, to see this, first of all, of course, you can see it directly. It's simply by expanding it as DKLs, as difference of DKLs. It's not one DKL, of course, because this can be either positive or negative, and I'll give you an example in a second. But actually, to think about it in terms of those Venn diagrams, which, as I said, I mean, you have to be very careful with them because not everything is interpretable as Venn diagram. Sometimes these are very confusing. There's actually a whole line of literature which is trying to generalize these Venn diagrams to multi-dimensions, and it's getting complicated simply because the inclusion-exclusion formulas, I mean, the interaction of n variables in general is getting exponentially complicated with the number of variables. Or if you want, the number of intersections here is getting exponentially large. But actually, so this is x, again, this is the entropy of x, this is y, and this is z. The intersection between 2 of them are the mutual informations. So in this case, I have 1, 2. This is x and z. This is x and y, and This is y and z, and there's another one, x and y somewhere. This. Okay. So I have three intersections, which gives me the mutual information. And actually, the synergy or the difference between these three is exactly this area, which is in the intersection of all of them. So this is why it is symmetric. So this intersection doesn't depend on which my condition. So it's in the information between minus the conditional information is always the difference in the mutual information and what's removed from it when I know another variable. Okay, so this is, of course, non-rigorous graphical way of thinking of proving the symmetry. Because we really want to prove it, you have to expand it in the DKLs or in the log expression and see what happens. Now, as I said, this can be positive and negative, and I promised you an example. So the best example of it in this notation, actually, most people actually call this minus the synergy. There's somewhat of confusion in the literature, because synergy, the meaning of synergy is that when components collaborate together. I mean, when you get more from the knowledge of the sum is greater than than its part in some sense, and that's what we call synergy. Then you get where three things give you more than each two separately, then you are synergistic. If they give you less, then you are anti-synergistic. So that's why they usually put a minus sign here, but that's very confusing. So essentially, the easiest way of synergistic cooperation is where you get something like y equal, let's say, x plus this. Think about them as even binary variable, bits. So this is a bit, this is a bit, and this is a bit. So the XOR is the sum modulo 2. I hope all of you know it. So this notation is what you call XOR, or exclusive OR, which is sum modulo 2. So 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, but 1 plus 1 is also 0. Okay? So, I mean, modulo 2. So it's, if you think about those as binary variables, this is a bit, let's say that x is some text, and z is a completely random bit. X is some bit random, some bit. So of course, if this is completely random, and I don't know z, y and x are not going to have any information. I mean, if I add random bit to some bits, I get random bits. Random modulo 1. So this is, for example, an encryption. When you do an encryption of something, essentially what you do is you XOR it with a random sequence, or with a pseudo-random sequence. And this actually makes it informationless. So if I see some, let's say, text and it's encryption, in principle there's no much information. But if I know the key, or if I know z, then of course I can XOR it again. Just add z again. If I add another z here, this will be just x. Okay. So that's why I can go back from the encryption to the original text simply by XORing it again with the key, with the random sequence. Okay. So in this case, this of course is also true for non-binary things, but it's easier to think about it. This is the simplest example. So if I add, and this is a special case of adding noise. I'm actually adding binary noise to bits, then I'm completely randomizing. So in this case, if z is random bit 0, 1, and all of them are 0, 1, so the information between x and y is what? If I don't know z, is 0. There's nothing there. I cannot recover. I see x and y, they look like two independent random sequences. Just as the information between x and z, and information between y and z. All of them are 0. As they should be, because all these three are the same thing. Now, so this is 0. But the information between x and y, when I know z, is what? Is whatever the information is actually 1 bit in this case. Because if I know z, x equals y. Okay? So in this case, it's 1 bit. It's the maximum information possible, which is the entropy of y or the entropy of x if you want. So in this case, the synergy is what? In my definition, if I put minus here, it's actually, so it's a positively synergistic. Okay, I confused it again, but sorry. So this is going to be positive, the difference. A negative, sorry. It's going to be negative, so the minus is going to be positive. Yeah, there's just full synergy. Each pair doesn't give me anything, but the 3 of them give me the whole information. So that's the full synergy in the case that I see 3 neurons like this. Each one doesn't give me anything, but together they give me all the information. Okay. Now, on the other hand, the other example for more is the simplest one that we already saw. If you have a Markov chain, let's say x, z, y, just to confuse you. If I have this Markov chain, it's exactly the opposite. So this is full synergy. This is completely anti-synergistic because the information between x and y is maximal if I don't know z. But if I know z, I actually cut the flow between them, and then information is 0. So in this case, I, x, y, z is 0. And therefore, this is always greater than this, and it's positively synergistic. So a Markov chain is the example of anti-synergistic in that case, because knowing the middle variable is actually cutting the information. I don't know what happened. Nothing flows if z is frozen. But in this case, so in this case, the synergy is negative. It's anti-synergistic. So this, and as I said, I mean, this actually turned out to be a very useful concept in neuroscience. Because in many cases, we actually want to measure the synergistic cooperation, let's say, of different cells or different neurons or different parts of the brain in terms of explaining things. So for example, if we have 2 neurons and we see that each one of them doesn't give me any information about, let's say, a stimulus or an action or whatever, something else which we measure, doesn't mean that together they will not give. They actually together they may give everything. Or that they may give, actually, it may actually happen that together they give me less information than each other separate. Everything is possible. And when you analyze, and we do those kind of analysis of how groups of neurons really influence different parts of our understanding of what we call the neural code, which is a very strange concept anyway. I'll talk more about it later. But so if we actually find groups of neurons just synergistically giving information, they somehow cooperate together, they're connected together. By the way, so in terms of graphs, this actually means that there's some hidden codes. So there's some W here, which give me information. So I actually get information about Z in 2 different ways. This is where they're actually synergistic. And they're going to be anti-synergistic in exactly this way when there is really Markov chain. But in this case, both x and y are giving information about W, and so on. So you can play with graphs like this, and it's getting more and more complicated the more variables you add. So I don't want to spend too much time on it. So this is just to clarify this issue. Now, one of the things we actually saw is what I call the data processing inequality, which is extremely important. So if we have a Markov chain, the information can only decrease along a Markov chain, which means that the mutual information between x and z, and x and y, let's say, cannot be smaller than the mutual information between x and z. I only lose information, and this is what I call DPI, or data processing inequality. Okay, so DPI, remember this. And this is essentially, it's going to play a very important role in what I'm going to say next, which is before I go back to the typical sequences. I'm not going to forget it. It's just, so that's something I didn't have time to say last time, but it's really very important. So DPI allows us to rethink the notion of sufficient statistics in a much more precise way. So if you remember, if you move along a Markov chain, which can be a very long Markov chain, you only lose information. And as I said already, you may or may not lose entropy. I mean, entropy can increase or decrease along the Markov chain, but the entropy doesn't tell you anything, because I can add noise between those processes, or I can do all sorts of funny things. I can reduce entropy by shrinking my space. I can increase entropy by adding independent noise, but this will not add information. So adding noise is not adding information. Usually just reducing information, but it can increase entropy. It does increase entropy. So remember this. This is why I usually try to avoid what some people call, never call entropy information. Entropy is uncertainty. Information is this mutual information or any extension of it. Now, of course, I can generalize this notion of information to many variables in several ways. This is what we call multi-information. But this is a dicey area. I mean, there are many different consistent or different ways of extending the mutual information to many variables. And you can see why. Because again, when you start to deal with more than 2 or more than 3 variables, we have this property of distribution, which you may have heard of, we call inclusion and exclusion formula, which is essentially how do you expand. So if I have n events, say more than 3, I don't know, I have n, they intersect in a crazy number of ways. And they're all, as I said, the exponential number of subsets here, exponential in the number of sets. And how do you add? So there is no simple expression that tells me how to calculate, say, the probability of an event. And so essentially what we do it is by a formula which is, in probability is called the inclusion-exclusion formula, which is essentially it's adding and subtracting terms, because some of them have negative values, some of them have positive values. And this is an exponentially, it's a very frightening, it's actually known as a Sharpe problem in computer science. I mean, in general, calculating things like this, the probability of an intersection of many sets is exponentially expensive in terms of the number of sets, which is bad news for anything who is trying to do calculations with it. It's actually provably Sharpe. It's very hard to approximate. And that's exactly the reason why mutual information of many, many variables is becoming a very dicey, but still you see that the chain rule of information is actually giving us some in positive quantities of the condition in terms of conditional information. So the chain rule of mutual information, which I wrote last time, how much information I have in n variables with respect to another variable y, this I can always break down into the sum of the mutual information between, let's say, I goes from 1 to n of xi to y conditioned on the previous ones. And when I equals 1, this is 0, which means there's nothing here. Okay? So this is and we know, so this is the chain rule of mutual information. This is always true. And we also know that all these terms are positive, unlike what I said last time, are non-negative. So by the way, so in particular, if I find one of the x's which actually captures all the information about y, I know that all the others are 0. So in that sense, if there are many, many candidates here, many variables, and I'm looking for the one which actually captures all the information about another variable, if I found one here, since all of them are positive, if one of them already equals the entropy of y, let's say, the maximum possible value, explains y, then it is sufficient statistic for y. And actually, in this case, it's going to all the other variables are not going to tell me anything interesting. Okay, so that brings us to this notion of sufficient statistic. So again, I'm just emphasizing this again. All these are non-negative. So this is actually good because, okay, I can expand if I have a collection of cells, let's say, and I want to see how much they tell me about some behavior. If I found one cell which actually explains why, I don't need the others. I mean, they don't tell me anything new. No need to measure them. So I don't know how many of you are familiar, let's say, with the book of Bill Bialik on spikes, called Spikes. You heard it and heard about it? Anyway, so one of the nice things they did, not only in this book, in a long list of papers, is actually explaining the neural code in a very specific case of the H1 cell of the fly visual system. And maybe you heard about it. If you haven't, you should. So in this case, they actually showed exactly that this one cell captures all the entropy of the stimulus. So in that case, they actually understand the code. They proved, that, numerically at least, that this particular cell captures all the information, so I don't need anything else.
Why do you need so many neurons?
No, actually, in the fly visual system, you don't need it. There are very few neurons. I mean, everything in fly goes through a very small number of cells in the visual system. I mean, something like 20 cells or less. And each one of them, we know exactly what it encodes. And the H1 is the one that encodes the horizontal motion, left to right or right to left, I don't remember. And so exactly, you know that this encodes the motion of bars in one direction. There's another cell that encodes the motion in the other direction. There's another cell that encodes the motion top down and up and bottom up and so on. So all those cells are perfectly well understood, and this is maybe the only real example where we understand the code, when we actually know what each neuron is encoding. And the way to prove it is exactly through this inequality. We actually show that in this case, one cell gives you all the information. So the others don't encode it, and actually they're completely orthogonal in this case. Each one of the cells is encoding different independent information. But that's very rare. In most neural systems, this is never the case. I mean, we have redundant distributed code, which is all over many, many neurons. We hardly, personally, I believe that it's essentially never the case that you can say this cell encodes this information. The face of Madonna, I don't know. This is nonsense. In the cortex, at least, in the human cortex. I don't think anything like this exists.
Why would it be different with the fly and human brain?
Well, then, because the fly is slightly different from us, but no, because there is some very effective or efficient evolution in the fly that really pushed it to a very narrow bottleneck of cells in the visual system. So all the visual, conic cone eyes of the, I mean, this it's not the eye. The visual system of the fly is very different. It doesn't have one eye. It has many, many photoreceptors. Each one of them something like order of thousands, and they're all funneled together into one ganglia of 20-something cells. So that's very different from our visual system. We actually have a fan out. I mean, from the retina, we're only expanding the number of cells. So it's getting more and more distributed.
So this redundant thing that we have in the brain is due to the structure.
Yeah, we are much more wasteful. I mean, we have many more cells, and of course, how the information is encoded in many cells is a different issue. But we hardly have this case that one cell encodes. We really understand what it encodes. Although some people claim that they see such things, it's usually completely anecdotal, and in the next experiment they don't see it, or they see something else. So any grandmother cells is nonsense as far as I'm concerned. But, yeah. Okay. Yes.
You said that if you have one term there that equal to one or more than one third that corresponds to not one third, to the information of y.
If one, since I know that this is smaller than the entropy of y, if I get, and they're all positive, so if I get one term here which actually is equal to the entropy of y, I know that this is the code.
And this is the sufficient statistic?
Yeah, in this case it's going to be even a minimal sufficient statistic. It's going to be a sufficient statistic. So I'm going to elaborate on this just a second. Okay, so when we talked about sufficient statistics, so I hate to write a long word. So we talk about sufficient statistics, we actually said, okay, So in statistics, if we have a parameter, I actually wrote it originally as a parameter, data, and statistics. So call it an S. And then I said that it's sufficient statistic if the other Markov chain. So now let me just replace it by Y. Okay, this is nothing, just by notation, because it's not necessarily a parameter. This was a parameter in a parametric distribution, but I want now to think about any variable, which can be not necessarily a parameter. So I have this chain. This, by the way, it's not necessarily a function, maybe a stochastic function, but there is a Markov chain like this. And we said that this is sufficient statistic if the other Markov chain is also true. So this is S is sufficient statistic if and only if these two Markov chains hold. So it's S statistic if this Markov chain holds, and it's sufficient sufficient about Y if this Markov chain also holds. Okay. Now, so in terms of mutual information, what does it mean? So it means that data processing inequality is telling me two different things here. So the first Markov chain is telling me that IXY is greater than RYS. Okay? This is the first Markov chain. This one. Okay? This is DPI. Okay? Now the second Markov chain is telling me that XY is less than IYS. Okay? So this is the first one and this is the second one. So of course they must be equal. So S is sufficient statistic of X for Y if and only if, because this was and if and only if and only if these two inequalities hold together. But in that case, this can be only if they're equal. If IXY equals ISY. Okay, so this is a nice information theoretic characterization of sufficient statistics, which is exactly what our intuition is telling us. It's sufficient if it captures all the information about Y, and it's a function of X. Okay, so it's some function or some map of X that captures all the information about Y. Okay, but now, so this you can find in books. I mean, if you read Cover and Thomas, where he talks about sufficient statistics, in chapter 2, I think, 2 or 3, depends on which edition of the book, you'll see exactly this definition of sufficient statistic. So if you want to check if a sufficient statistic, if it is sufficient statistic, you can just show it. Well, actually, this is not so easy to check, because calculating the mutual information can be hard. But actually calculating, so you have a much more practical way of checking if something is sufficient statistic. It's the Neyman factorization. So if you can write it with factorized joint distribution using the Neyman factorization, then it's a sufficient statistic. And then it's very easy to see from the Neyman factorization that in this case, if there is Neyman factorization, which means that Px given Y can be written as some function of X times some other function of S of X and Y. This is if this is true, this is Neymann's factorization. Factorization lemma. So if this is true, plug it here, and you see immediately that it's trivial, simply because the log you're going to have above and in KL, you are going to have the same factor H in the numerator and the denominator, and it's going to cancel. So the mutual information is independent of X other than this, and this is why it's going to give you exactly. So it's trivial to show this from Neyman factorization. This is very simple, but I just proved it using DPI. But So it's a good exercise to try to prove it for yourself. But actually, DPI gives us much more than that. So remember that we, in general, just having one sufficient statistic, I mean, a sufficient statistic is trivial. You take all your samples, you take all your data, it's a trivial sufficient statistic. But that's not helping much. So we want sufficient statistics which actually reduce the complexity of our observations, like taking the sample average or sample mean, sample variance or things like this. So I reduce n samples to 2 numbers or 1 number. Then it's really helping us. So we want what we call minimal sufficient statistics. So remember, how was minimal sufficient statistics defined? So minimal sufficient statistics, minimal sufficient statistic was something which was the simplest possible, or the coarsest partition of the data in some sense. And so, but that sounds like a very flaky concept. How do I check it? I mean, how do I test if something is a minimal sufficient statistic? So that's something which personally bothered me for a long time. I mean, I first heard about sufficient statistics a long time ago, in the 70s. And then I really, since then, I was completely, captured by this notion. I wanted to understand it better. And I'm somewhat obsessive about it. But anyway, and what is really nice is that if something is a minimal sufficient statistic, so it must be a function of any other statistics. So a minimal, let's say t, is a minimal sufficient statistic if this Markov chain also holds. Which means for any other sufficient statistic, t is a function of it. Okay? So t is a minimal sufficient statistic. And this is just any sufficient statistic. Okay? So what it means in terms of DPI, what it means? So in terms of DPI, I can apply DPI not only to this chain as I did before, but also to this chain. So what do I know now? So for minimal sufficient statistics, x t must be less than I x s for any sufficient statistic s. So this looks like too many s's. Okay? So this is for any. Okay, so in some sense, a minimal sufficient statistics must minimize the mutual information on X among all the sufficient statistics. Okay? So a minimal sufficient statistic is going to be, I want to minimize, if I want to find a really minimized statistic, I want to minimize over all possible S's, I XS. So the arg mean of this is going to be this t, such that ISY is equal to IXY. So this is a better definition, or slightly better definition, of a minimal sufficient statistic. Minimize the mutual information on the variable x without losing information on y.
It's because of throwing away all the noise and only taking what's relevant.
So take only what's relevant and ignore the rest. Yeah, that's the very simple intuition behind it. Okay, but that turns out to be an interesting problem, because essentially what it tells me, okay, if you want to minimize something under some constraint, and the constraint is that the mutual information is not lost, how do you solve such problems? Constraint minimization or constraint optimization in general? Lagrange multiplier. You should say this in the middle of the night. This is something you should know. So unless I have some technical problem with Lagrange multiplier, sometimes I do. In this case, I don't. I put a Lagrange multiplier. So this is essentially like minimizing. And actually, I don't really care about t. What I care is the map from x to t. I really care. So in general, I want a map from X, which may be stochastic. I'm actually going to call this map the encoder of the statistics. I mean, this is something which is telling me how to calculate the statistic from the data, subject to this constraint. So essentially, it's minimizing this type of functional. Minimize all the over all possible maps. Over all possible maps. Minimize the information with respect to the data subject to a constraint. So I put a Lagrange multiplier, which I'm going to call beta, for reasons which will become clear later on. A constraint on this. So this is an operational definition of minimal sufficient statistic, as long as I actually make sure that the information is really preserved. But we saw already that this is not always possible. And we know that sufficient statistics, non-trivial sufficient statistics, exist exactly for the exponential families. And unfortunately, the exponential families, they're dense. If I allow the exponent to be as complicated as I want, it's a dense family. But in general, it's not. In general, it's not possible. For example, I have a mixture of Gaussians, or if I have a mixture of Poisson distributions, or I have a mixture of exponential families. It's not an exponential family. Okay, so I relaxed it a little bit. Yes. Yeah, so that's something we already talked last time, so I'll say it again. In principle, it should be, yeah, you're absolutely right. It should be S1. Yeah, you are really very sharp. It's all right. You always ask the right questions. Okay, so it's ISY. And of course, actually, I should also put here I minus IXY. If you remember, with Lagrange multipliers, I actually put. But this is going to depend on my encoder, and this is not, so this essentially is irrelevant for the same reasons I talked about last time when we talked about Maxwell entropy. But this is important. I mean, if this, I want this information to be equal if I really want minimal sufficient statistics. But now I can relax this. Yes?
What breaks in the optimization? Why does a non-exponential family distribution fail to have it? You have a formula for the minimization. So what happens? Like they go to minus infinity or something?
So okay, I'll come back. I'll come to this. This is a good question. Let me answer it in a slightly longer way by solving this equation. Okay, so this principle is essentially, okay, take X, squeeze out of it all the information that you don't need, that doesn't tell you anything about Y, and what's left is a minimal sufficient statistic. That's what it means. So my intuition was that you really squeeze the information through some sort of a constrained bottleneck. I mean, it's in some sense of, I take out only the information from X which is relevant for Y. That's why I called it the information bottleneck. So I don't want to dive too much into it. I think I should mention it. The information bottleneck principle or method. So the question is how to solve it in general. I mean, does it give us any concrete recipe? I mean, how to calculate this map? And as I said, it's giving me not T or not S. It's giving me this encoder. Now this turned out to be interesting. I just write here without proof.
Is it really a probability function or is it just a function?
No, it's a probability function. So for reasons which will become clear later on when I talk about rate distortion theory, information theory, so wait another 2 weeks towards the end of the course. so we can solve this, surprisingly. And the solution turns out to be interesting. So if you just try to minimize the information about a variable without losing information about another variable, it sounds like a very plausible recipe. So just before the break, I'll write the solution. So it turns out that this is feasible, and the solution is pt given x, the encoder must have this form, p of t divided by some normalization, which depend on beta and then x, never mind that, some partition function. And then surprisingly, e to the minus beta, the KL divergence between py given x and py given t. This is the expression for the encoder, for any value of beta. And the decoder, so the decoder is how do you, which is here, how do you, what is this? How do you decode y, or how do you predict y from this compressed representation of x? So the decoder, as I usually call it, is simply given by what it should be from the Markov chain, which is just erased. Sorry. So this is what? So just looking for the Markov chain, it should be the sum over x, p of y over x, p of x given t. So you see that these two equations are coupled. The decoder appears here, and the encoders appear here. And this I can actually write through Bayes' rule as py given x, pt given x times pt over px. Okay, so this is just Bayes.
The opposite. The denominator should be p of t.
So yes. Sorry. P of x times p of t. Of course, I should also tell you what is p of t. So again, p of t is simply because it appears here. So it's of course what it should be is simply p of t given x times p of x. So these two things you could simply guess from the Markov condition. This is what it should be. It cannot be something else. But it turns out that those three equations are precisely the things that minimize this Lagrangian, or this is what we call the IB Lagrangian. So this is the ideal Lagrangian. It can be thought as a function of the encoder or the decoder, and that's the only solution. I mean, that's all the solution must satisfy this equation. So this is sometimes actually I can write it in a slightly different way. I can write it as p of x given t equals p of x over z of beta e to the minus beta this scale divergence and p to the encoder. So this is again this is the encoder. This is the decoder. We'll make sense of these names later on. We'll talk about coding. But this is the encoder of the representation. This is the decoder of the representation, and this is simply the sum over x, p of y given x, p of x given t, and these two equations just contain each other. So and of course, in order to solve them together, I need to set what we call solve them self-consistently. So this should satisfy this, and this should satisfy this. And of course, these kind of things you can prove in this case that if you iterate them, start from some initial guess, whatever it is, and simply iterate. Start with some initial guess for the encoder, plug it here, and then plug this here, and so on. These iterations, this is what we call self-consistently solving. This is something we do all the time in neural networks and physics and whatever we want. We self-consistently solve these equations, and this actually converges to the optimum. To an optimum. Unfortunately, it's not a convex problem, and there's no unique solution to this. that there are many solutions, but we'll talk about it much later. This is the beginning of a big story for me, at least, which seems to be related also to understanding of neural networks and deep neural networks and deep learning and brain also. So I never taught this in this course, so this is a private matter, but it turns out to be important. So I'm going to talk a little bit more about it in the context of deep learning, but if you want to know more about it, we have other opportunities. Yes? Here? I switched the order. Because I switched the order, I left P. I simply divide this equation by Pt and multiply by Px. This is Basel. So I moved from the reverse decoder encoder in some sense. Instead of saying how x is mapped to t, I'm saying how x is conditioned on t, or how t is mapped back to x. And this allows me to have only two equations. And now we solve them what we call self-consistently. Okay, and we can prove, well, I'm not going to do it here, that these iterations converge, actually very quickly. And if you think about it, so what happens here? Essentially, I'm taking just 1 minute. This is essentially some sort of a distance or distortion. So it's telling me how well you predict y from t compared to the true prediction from x. Now, if I'm perfectly okay, I have a sufficient statistics, then this is going to be 0. Because my prediction from t is going to be the same as the prediction from x. I'm not going to lose information. But if I'm only approximately sufficient, then this is going to be a positive number, which actually measures how distorted your prediction is, how bad is your prediction from the representation, from the statistic, with respect to the true data. Okay? So this is going to be an interesting quantity. It's again our old friend KL divergence. But the KL divergence now appears as some sort of a measure of how well I predict from a representation. Okay, so I'll leave it here. We're way into the break. And I want to go back to typicality in the next hour. Any questions on this? And if you don't have questions, you didn't understand me. I just opened the door for something very, very complicated. But I just wanted to give you a sneak preview of something much more interesting. So we say modulo 2. Mod 2, which means when you get to 2, you will 0. This is the sum in a binary field. Okay. So if in this example, x, y was x plus b, and z was a random bit. So in this case, the sort of something with a random bit is just a random bit. So if I don't know z, I don't know anything. can be either 0 or 1 with 3 probability.
Okay, okay.
So in this case, IXY is 0.
Yeah, and IXY given 0, is 1.
Yes, because if I know Z,
Yeah.
I can simply show with it I have all these.
Yeah, yeah. And you call this if X, Y, Z, I know X and Y, Z, so the mutual information is 1. We call this synergy.
So in this case, there is synergy. If I know Z, I suddenly know everything. If I don't know Z, I don't need anything.
Okay.
So they cooperate. They give you more information together than separately. Okay. Any pair doesn't give you anything.
Okay.
But the three of them gives you everything.
Okay, okay.
Okay. So this is full teamwork. The synergy connects. Yeah.
לא הבנתי מה כל הסיפור הזה. כן. כאילו, איך... אוקיי, זה כאילו בעצם אומרים...
הרי שסטטיסטיקה סטטיסטית מוגדר כמשהו ששומר את האינפורמציה.
אוקיי, אז מה...
ראינו שמינימום סטטיסטיקה מוגדר כמשהו ששומר את האינפורמציה ורק אותה.
כן.
רק את האינפורמציה הרלוונטית.
אז מה זה אומר האינפורמציה? מישהו אינפורמציה לפי זה?
אז אני שאומר שם x ל-f במקרה הזה אותי. קודם כל זה אומר שמכל הסטטיסטים הספיקים תנתן את הסטט ביותר. נכון? כי אם הוא קטן מכל אחד אחר, אז הוא קטן מכל סטטיסטים מספיקים. מכל אלה שהם סטטיסטים מספיקים, אם אני מזער את זה, אני אמצא סטטיסטים מספיקים למעלה.
למה שהמיוטשל אינפורמציה יהיה מינימלי? הוא אומר לי...
זה אומר לי, אל תשכוח שום דבר לא חשוב.
במובן מסוים, אבל בשביל להבין מה חשוב ומה לא, אני לא צריך לדעת גם...
נכון, היה כאן תנאי ש-S הוא סופיסטנט סטטיסטי. על Y. זאת אומרת, זה התנאי הזה. כן, התנאי הזה שאומר לך את Y.
אז בעצם הגודל הזה אומר לי, אם הוא קטן, אז...
אני רוצה שהכי קטן שאני יכול מכל אלה ששומרים את האינפורמציה Y.
וזה אומר לי שאני יכול לפחות לשחזר את X.
לא, אני אומר שאני יכול, אני שוכח את X במובן שלו.
כן.
אני זוכר רק את החלקים של
X, אבל עדיין sufficient.
רק את החלקים של X שהם משוזרים לכל. וזה נותן לי סטטיסטיקה סטטיסטית מינימלית.
ואז הגדרנו את זה מפה, אבל למה איך הגענו
אני לא רוצה את הפונקציה, אני מספיק לי שיש לי מיפוי סטטיסטי. יש מעצם הרבה פונקציות. אז אני יודע שהפונקציה היא לא יחידה. כלומר, אני יודע שכל פונקציה אחת הזאת של סטטיסטית מספיק לא סטטיסטית.
אבל מה הכוונה בהתפלגות כזאת של T בהינתן X?
אז הוא אומר, תגיד לי סטטיסטית, איך אתה מנפה את X סטטיסטית? כלומר, בהינתן X, תגיד לי מה הערך של T, אבל באופן הסתברותי. ואתה רואה שהתשובה היא באמת הסתברותית. אתה רואה שזה אקספוננציאלי, כל עוד בטא הוא לא אינסוף, אבל לא פונקציה טובלית.
אבל אם אני, במובן מסוים, אם אני לא אהיה בנקודת מקסימום של ההתפלגות הזאת, אז זה לא ספישנט? זה לא ספישנט?
אם אתה לא גם מינימום,
אם אני לא במינימום, אז זה לא
מינימלי.
זה לא ספישנט.
לא, הוא סופישנט.
הוא
יהיה סופישנט אם התנאי הזה מתקיים. אבל אם התנאי הזה לא מתקיים, הוא רק מתקיים בכלום, אני אהיה מה שנקרא אפרוקסימטיבי. אני הכי טוב שאני יכול לעשות את התנאים. ואנחנו נראה שזה מתחיל להיות מעניין.
אוקיי, ואז עשינו לגרנג' מדבר, אבל זה רק הפתרון.
זה הפתרון.
בלי להסביר.
אבל אתה רואה שכאילו זה make sense. כלומר, שתי המשוואות האלה הן טריוויאליות. הן לא מתקיימות לאף שזה לא מתקיים. שתי המשוואות האלה פשוט חוקי הסתברות. זה מרקוב צ'יין. זה מרקוב צ'יין, אז ההסתברות בין Y ל-T חייבת להיות שהתנאי הזה, המרקוב צ'יין הזה מתקיים. זה דורש הוכחה, אני פשוט לא היה זמן לזה, אין זמן. אתה יודע שמתקיים גם YXT וגם YTX. כיוון שמתקיים התנאי הזה, אז זה חייב להתקיים. וזה סתם מרג'ינל. כלומר, כאן אין שום דבר. השני האלה חייבים להתקיים. והאנקודר הוא הדבר הלא טריוויאלי. הוא נפטר מתוך. עושים הזמן לקרוא לזה שזה עובד. אבל אני לא צריך כרגע לראות את זה, אני רואה שיותר צללים מזה באיזשהו שלב.
תודה.
יש לי מאמר עם אלעד שניידמן, ואלעד פשוט לעבוד בזה הרבה שנים אחר. יש לנו מאמר משותף אחד, זה ביוני שלי, אתה הבן של ירון?
מה?
לא.
לא, מה?
I'm sorry,
לא, אני confused with somebody else.
All right. So I know if you are not satisfied with what I said, you want to hear more about it. Maybe. Don't sound busy. I'm going to go. I'll come back to this, I promise.
Is it part of the...
לא, תשאלי. אנחנו פה בשביל לענות לשאלות. What's the question? ברמה של מה שאמרתי עכשיו, כן, אבל לא יותר. זאת אומרת, אני לא אעשה לכם מזה עניין גדול. אנחנו עוד לא החלטנו איזה סוג של בחינה תהיה לכם. אם זה הולך להיות בחינה אמריקאית או בחינה לא אמריקאית. מה שיקל עליי מאוד אם זה יהיה בחינה אמריקאית, אבל אני יודע שחלק מהתלמידים לא אוהבים את זה. בעיקר בגלל שהתאריכים של הבחינה הם קצת בעייתיים. אז בואו נדבר על זה שנייה. Sorry, so there is an issue of what type of exam I'm going to give you. So last year I had twice as many students because we had 2 years together. And for the first time I actually tried a multiple choice exam. And I must say for me it was much easier. I'm not sure that all the students were happy with it, but it actually, I think that most of them were more or less satisfied. I mean, it's hard to argue. I don't have but of course the tricky part is to write the exam correctly, fairly. And that's, so there's a lot of work for me in writing the exam, but it's much easier to check it. So there, and some people actually like it. Usually the people who are not good at multiple choice exams are the more creative and the slightly, ADD type, but they often are the best students. So it's not. So I know that there are some people who for this type of exams are not optimal. Some others really like it. The alternative is, the old style. 3 out of 4 questions. Each one of them has some easier to harder parts, and you just have to show me that you understand the concept. You can apply them in some simple and maybe less simple exercise, such that allow me actually to grade you in some normal way. This is the traditional way of my exam, at least. I mean, I always had this structure: 3 out of 4 choice, and each one of them has something like 3 different sub-questions. Easy to hard. Now, in general, so this is going to be easier for me in some sense, but harder because usually this type of exams raise all sorts of questions after the exam, during the exam, and then I'm not here, especially. It's going to be hard to satisfy your questions. So currently the date of the exam is somewhere at the beginning of March. Unfortunately, I'm leaving right at the end of the semester on the 27th and 28th of January, and then I'm back for about a week, and then I go again, and then I'm back at the end of March for a week. No, I'm sorry, at the beginning of March for a week, and then I go for another 5 weeks or something. So come back only the end of April. So if you want me present in the exam, and I think it's important that we present in the exam, especially by writing. We chose this relatively late date because of this. Because right after the end of the semester, you didn't want it. At the beginning of March, which I could do, somebody else didn't want it. I could do it 1, 2, 3, or 4 of March, something like this. None of you could do it. At least it was not pushed. So it was pushed to April.
What? April?
Yes, no?
No. I'm thinking from March.
It's
On the
March.
4th of
March.
March.
Okay, March, yeah. Okay, sorry. So you could do it in March, but you couldn't do it in
It's the
February.
midnight shift.
No, it's alright. Yeah.
4th of
Early March. Yeah. So I still have to just make sure that we agree as much as we can with some sort of soft constraints on what type of exam you want. So, you can look at the exam from last year. It's available, Neely can give it to you, I think. So I cannot repeat those questions, or maybe I can, but
we don't mind.
But actually there were two different terms, and both of them were similar, and all sorts of variations on the same question. But sometimes those multiple choice questions are tricky. I mean, they can look like very similar questions, actually the answer is different. So it's enough that I change the choices to make it a very different question. So these are not necessarily easy exams. I mean, they're not easy, but I think they were fair. And people who really understood the material got in the high 90s, and those who really didn't understand got below 80. So it was a good distribution as far as I can tell. I think, but I know that it was not fair for all of you. There were some very good students who got relatively low grades because they were too creative. Something about different options of definition. Maybe had other ways of thinking about the question. And so that's always the problem with exams. That's why I hate exams. I hate to take exams. I hate to give exams. And that's, I think exams are necessary evil.
What is the percentage of the exam? The percentage of the exam.
So it's something like 30% of the grade or something. More. No, it's 50%. Most of the grade. You can't pass this course without the exam, if that's what you want. No, the exams are important. But I know that you are PhD students and you don't really. Still, I think that sitting before the exam and actually going through the material and organizing it to you for yourself, solving all the exercise again and so on. This is what I really want. I don't care about the exam. If you can promise me that you do this, then I can cancel the exam. But I know that you don't, if I cancel the exam. So you have to think that there is an exam, and take it seriously. Now, I'm trying to be as flexible, as fair as possible. But I know that exams are always unfair in one way or another. So anyway, you don't have to answer now, but I need to know by the end of next week, let's say, what type of exam you prefer. Okay? Look at them, look at the two types of exams. Neely can give you old copies and decide for yourself. Each one of you. Okay. No. No. No, unfortunately, that's winner takes all, you know. Okay, now it's a hard decision. But there may be multiple versions of the exam during the class. I mean, so anyway, so this was opening the door for something which you'll see is even much more important. But I want to come back to the bottleneck method after we talk about the coding theorems of Shannon, because they are in some sense in the same spirit. So I started to talk last time about typicality. And I said, okay, so if we have a long sequence, a large number of variables, not necessarily temporal sequence. There can be samples of sound, or they can be pixels of an image, or frames of video, or words in documents, or who knows what. There are many, many different types of objects like this. And all of them are things we're actually looking at. So in some sense, there's something very fundamental about entropy. So first of all, we know that if in some way there is some structure in the data, so now I'm saying something important, but those who are here for the first time will not get it at first. If there's some structure in the data, for example, the IID is a very simple structure in the data. That's simply independent, conditional independent list. But they can be related to each other. For example, a Markov chain. So each one can be dependent on the previous one. Or they can be what we call Markov random field. I don't know how many of you heard about it. For example, an image, if you look at an image, there is some connection, local connection. I mean, nearby pixels have nearby color and have similar color. That's true for all pictures unless they look like nodes. I mean, so meaningful pictures usually have structure, which means that there's something which I can see from a long distance, actually. So nearby pixels have similar probability. So in some sense, I can predict the value of a pixel, the color of a pixel, just from the neighborhood. So this type of model is usually called Markov random field. And there are many other things like this. For example, if I look at text, I can think about the words as having a Markov chain or Markov condition. Each word depends on the previous words. The probability of seeing a word depends on the previous word, on the neighborhood, on the next word. There's some structure around it. Words in language don't look random. They depend on each other. Okay? And so on and so forth. Actually, all the interesting structures that we see around us, whether natural or artificial, I mean, images, texts, DNAs, proteins, whatever you want, they all have some local structure in the sense that I can actually factorize the probability of a certain value if I know something about the neighborhood. So this is a very general principle. So usually, the way we write it, this is also the philosophy behind all this field that is called probabilistic graphical models or Bayesian networks and all these things. So essentially, there is some, for each variable here, I can write it as a product of the probability of this variable, condition or something which we call the parents of this variable. Where I goes from 1 to n. Now, the parents is a concept that we take from graphical models. So essentially, all the variables that affect its value. So for example, in IID, so examples. So as IID, it is trivial. Just p of xi. Okay? Condition or something. So the parent is a null set. Or maybe just the parameter of the distribution. Okay? So this is trivial. A Markov chain, if I have x1, x2, x3, and so on, in this case, the product, so the Markov chain, or actually first order Markov chain, this is simply the product of the probability of each variable condition on the previous one. And with the right interpretation of the boundary conditions. Doesn't matter. So this is a first order Markov chain. Second order Markov chain, each one depends maybe on the two previous ones. So then the parents will be the two previous variables, and so on and so forth. A Markov random field, the parents depend on the local neighbors in the image. So let's say I have a pixel, this, and I'm looking at it as a grid. So this pixel has 8 parents around him. So if I know the value of the 8 parents, I can predict the value of the pixel with some probability, of course. It's not always true, and so on. I can have a more complicated model like this. But all the models for which I can factorize it like this is what I call structured data. So there is structure. Structured variables.
Are there examples of
Sure. I mean, I can have, for example, a spin glass. I mean, I can have binary variables which depend on very far neighbors. So there is fully connected interactions.
Every distribution can be factored if you define the...
Right. So it's structured if the complexity of the parents is bounded. So for example, the number of nearest neighbors is finite. Or so you're right. I mean, any distribution can be factorized like this. I showed you already how. But if the complexity of the parents is growing with the size of the data, then it's unstructured. But if the complexity is bounded, or at least statistically bounded, I mean the probability that I'm actually influenced by a pixel in the other part of the universe is very small. I am, but you know, we are living in an entangled universe. But I can neglect this, the effect of a pixel 10 light years away. So then I'm in a structured universe. Now physics, the laws of physics give us a very strong structure. Locality in time and in space, which is an extremely important principle in physics. So actually all of the basic laws of physics, let's put quantum mechanics aside for a second, are all structured and even Markov. I mean, the state of the world now depends only on the state of the world in previous time. Nothing else. And also in space. I mean, the locality in space, in 4 dimensions or whatever it is that you believe we live in, is also very, very important. So the fact that there is physics, which seems to work pretty well, is because of this structure. Because there's structure in space and time. And I can give you a whole lecture about it. I don't want to. This is just to know that it's not just a far-fetched idea. I mean, this is something we use all the time. Yes?
What do you do with the complexity of the parents?
So in all the examples that I gave you, here there are no parents. Okay, everything is very simple. Or maybe there's just parameter, which is common to all of them. Here there was one parent, the previous one, and it stays one. In the Markov random field, there are 8 parents, let's say. I look at 9 pixels, and the middle one is predicted from the 8 neighbors. And it stays 8. This is just a Markov field. This can, of course, I can do it in any dimension. In a hidden Markov model, for example, which is slightly more complicated because I don't know the hidden states, but observations are highly correlated because they are linked to, because the states are correlated. And so hidden Markov models like that, this hidden Markov random fields are like this, or what we call, there are all sorts of there's a zoo of names and models which have this structure. All of them have this. Some of those parents may be hidden. I mean, not exclusively observed. So that makes it hidden variable model. But hidden variable models are still local in some very profound sense. Okay?
What do you mean
No, non-local means that I have a high distribution of being correlated with something which is very far away from me. Not in space and time. Let's say if something that happens on the other side of the universe affects my life right now, it's a very non-local theory, I mean, in some sense. And if it happens also in different times, I mean, if something, it can be non-causal, for example. If something in the future affecting my behavior now, then we call it a non-causal model. If something in the past, very far past, still affects my life now, it's also very non-local. Now, I don't want to get into this philosophy. But what we mean is that the number of variables in the parent is bounded, okay? Universally bounded. That's what we call structured models. Now, it's a whole field. I mean, there are people who make a career of learning structured data. Language is a very good example and a very complicated example of structured data, because there are correlation between words in text which are not all local. For example, I know, okay, so a sentence, for example, is a very structured object. Words are related to each other in a very, very specific way. There's grammar, there's syntax, there's all sorts of things. But actually, there are correlation between words across sentences. Of course, if you read a book, there can be very strong correlation between the beginning and the end of a book. Suddenly, the same words appear, the same. Usually, this is a very common theme in romans, in books. I mean, they end and start with similar things. Okay, but this can be as far as I want. I mean, so there are correlations in text which are far more non-Markovian. But usually we assume that this correlation of this information is decaying with the distance, decaying fast enough with the distance. And that's already structured. So a Markov chain, for example, is also, so there's a correlation, as we saw already, the information between x3 and x1, if I don't know x2. And so on, and information actually decaying exponentially. So locally, what I call structured models are not necessarily uncorrelated along distance. But the worst example of unstructured data is what we call spin glass, or this nature of models, which everything can be affected by everything else in the same way. There's no meaning to distance. Okay? No neighborhoods. Okay? So anyway, so such structured models, we saw already that this limit, so this is a very soft way of telling this. We can be a lot more rigorous about it. But this limit of minus the log of the probability exists in some sense. And this limit of the probability of a long sequence of observations is going to factorize, of course. So it's going to be minus the sum of over i's, the log probability of xi given its parents. What I mean, again, by parents, I mean that variables, the other variables that affect it, on which it may depend. And this approach, and this limit, and the 1 over n, this log, in the limit of large n, okay, so this equals to this, and in the limit of large n, this is going to converge because it's a sum of conditionally independent numbers. So this is going to converge, and we saw that at least in the case of IID, it's converging exactly to what we call the entropy of x. Okay? No, I mean, that's what I need. So if this is true, then taking the log is going to bring it into the sum, and to multiply anything. Okay? So so this is going to, if this is under some very specific technical conditions, which we usually call ergodicity and stationarity and things like this, which I don't want to get into. Those of you who know something about it can imagine what they are. Essentially, it's actually the condition that guarantees the existence of this limit. And this is absolutely true for IID or for Markov chain with fixed transition probabilities and so on, or Markov field or anything. So this is true for essentially all the things that we care about: images, signals, text, and so on, DNAs, proteins, anything that has structure. Okay? Now, and so we define it to be the entropy. And this is one number. Not that each sequence is converged to another number. If under those conditions that this factorization actually holds, if this is true, this is a very big if. If this is true, there is what I call structured data. This is true, where those probabilities are independent of I. I mean, so there's no index I here. There's only index I inside. Okay? So I cannot change my rules everywhere. If I give you a neighborhood, there is a given probability of the value of I. And if this is true, then this is true. Then there is one limit. And this limit is what we call the entropy, or the Shannon-Macmillan Breiman entropy. Okay? So this is from now on, this is my definition of entropy. Take a very long sequence and take the limit of the log of the probability. So you can do it yourself in an exercise, calculate the entropy of a Markov chain. Of course, you need to know the transition probabilities, I mean those probabilities. And if you know them, you know everything you need. And so on. Okay? Now, the interesting fact about it, really it's a profound fact, I mean it's important, is that if I know the entropy, in that sense, when the sequence becomes long enough and the number of variables grow, then essentially all the sequences converge to this limit, except a marginal, a negligible number, which could be called the non-typical sequences. Okay, so that's really the important part. Actually, this is nothing surprising at this point, because we have been talking about this limit, I mean, the law of large numbers all the course. I mean, this is really what saves statistics. The fact that sums of independent or conditionally independent things converge to their expectation. Exponentially. I mean, like, it usually, this sum of logs looks like a normal variable which grows like n, and with the standard deviation which grows like square root of n. So if I divide it by n, it converges like 1 over square root of n to a delta function. So that's all. That's all there is there. That's really the key. This is really the fundamental fact on which statistics is based, and on which our world is built, in some sense. I mean, there's this fact that things tend to average for large numbers. Now, we want to So we want to specify this more precisely. So essentially, what we're going to say is that within an epsilon of this number, almost all the sequences lie. So I am going to define a set a set of sequences, and again, those are in general what I call structured data, as a function of epsilon, as all the sequences such that the probability or the log probability allow me just to be short. So a log probability of the sequence is somewhere between age x minus epsilon, that doesn't matter if it's greater or equal, age of x plus epsilon. So for any epsilon greater than 0, and this is the same epsilon. So essentially what I did here is, this set is the set of what we call all the epsilon typical sequences. Which means that for these sequences, the log probability over n is close up to epsilon plus minus epsilon to the entropy. Okay? So it's clear what it is? So these are the epsilon typical sets, epsilon typical sequences. Just definition. What I mean is true.
No, I mean, they converge always.
No. So now comes the statement. So this was just a notation. I'm counting the set for which this log probability is close up to plus minus epsilon to the entropy. Okay? Now the theorem, which you can get for yourself, that this set contains almost everything in some sense. Or the probability of xn to be in A epsilon, this A epsilon. Yeah, I don't even need the set here. A epsilon. To be in A epsilon is what? It's close to 1. So it's actually greater than 1 minus epsilon. This is the interesting theorem. So essentially it's telling you, or some function of epsilon, that if I am looking at this set, almost all the sequences are in this set. Okay, so that's interesting. But of course it's obvious, because what happens is that you get this Gaussian converging. I put epsilon, if you give me n large enough, so all of them are going to lie inside in some sense. So actually I'm not very accurate here, but that's essentially the statement. This is a function of n. N is important here.
Just without the limit of n goes to infinity?
No, this is for n, a given n. So for a given n, the number of sets that are epsilon close to h is essentially all of them. So which means that, okay, there is, remember there's this epsilon, so there exists an epsilon of n. So really, to say it correctly, for any epsilon there exists n for which this is true, for any n larger than this n. So you can think either at epsilon of n or n of epsilon, okay? So this is really the correct statement. For any, so you really want to be like mathematician, for any epsilon greater than 0, for all epsilon greater than 0, there exists n of epsilon such that for any n greater than this n of epsilon, this holds. Okay? So this is just like infi, I need n to be large enough to actually push the Gaussian into this limit, such that the probability of the tails is smaller than epsilon. So what you already know, so the idea of the proof is really very simple. You know that this log probability is going to converge to the entropy. And you know that the tail, the standard deviation is going like 1 over square root of n. So if I put epsilon as the probability of the tails, how much is left out of this interval? If n is large enough, I can always squeeze the Gaussian into this interval. That's the whole thing. Okay? So essentially, there's nothing more than that. I can write it in a very sophisticated way, but that's all it is. Okay. Yes.
Why do we need structure? I mean, where?
No, but that's very interesting, because it's telling me almost all the sequences, if they are long enough, are typical.
But you're saying this is only true for structure.
Yeah, I need a structure. Because I need this to be a sum of conditionally independent numbers. I need to use the large number, the averaging theorem. I mean, I need to use the fact that I'm adding independent things. But this independent thing can be conditioned, so I don't care. Once I condition on the structure of the data, they're independent. So they look just like adding random bits or something like this. Okay? So but that's an extremely powerful statement. Why is it so powerful? Because it tells me essentially that the cardinality of this set is approximately 2 to the n hx. It's very close. So this is a slightly more complicated statement I have to prove it. So essentially it means that up to epsilon, all the mass is in this set. And not only that, the probability, why is this true? Because the probability, because in this set, the log probability is essentially equal, is age. Or in some sense, or the probability of all those sequences, probability of all the sequences in this typical set are essentially up to this epsilon. So in writing this in just in a slightly, I take the exponent of this. It tells you the probability is between 2 to the minus n age minus epsilon plus epsilon, and 2 to the minus n age minus epsilon. This is what it tells me. It's the same thing.
This 2 comes from the basis at all?
Yeah. Sorry, this is log 2 unless I say otherwise. Okay? Doesn't really matter. So this and this are equivalent. Yeah. If this is true, then the probability of all the sequences in the set are essentially the same. It's very close. So this is what I mean by this. But if all those sets have equal, if those elements have equal probability, the size of the set is simply 1 over the probability. This you know already. So this is the size of the set. Up to the epsilon, that's why I write it here. So it's plus minus epsilon in the exponent. Okay?
N of epsilon and
And you're right.
also be very large.
You're right. That's a very good point. Epsilon is inside this n, so there's a factor of n epsilon. So for this to be interesting, epsilon must go faster than 1 over n to 0. Yeah, you're absolutely right. But you can do this. You're right. There's an n epsilon. So epsilon should be. But fix epsilon. If you want epsilon to be 1 over 10 million, okay, fix it there, and then look for n large enough. But then it tells you essentially in this class of typical sequences, or typical patterns, I can call them. Patterns much better than sequences because they are not necessarily sequences. All of them are equally likely. So the probability of seeing this image and the probability of seeing this image or this image is exactly the same if they are large enough. But this is funny, yeah. I think this is very special. This is as special as this one. So, okay, so there are all the large images, all the large sequences are essentially the same probability. Okay, this has, as I said, is going to have a very profound implications. So, and remember, we're talking about maximum entropy at some point. Why maximum entropy is a good thing? We're starting to maybe develop some equation. I'm missing one person here. This guy was sitting here. What's his name? ask me all sorts of questions about it. Never mind. Unfortunately, I have this photographic memory. I remember where every one of you sits, and usually sit in more or less the same place, which is good. But then, if somebody is missing, I have a hole in my picture. Anyway, so yes.
The conversion to
No, I gave this intuition. I thought. That's what I just said. I mean, so essentially, this is a product of independent factors. Okay, the log of it is a sum of independent factors. A sum of independent factors from everything we said so far in the course. If I average it, it's going to converge to its expectation with width of the distribution, which goes like 1 over square root of n. That's it. Everything else is just mathematical details. This is what you have to remember. Okay. And you know how fast you can play with things like Chernoff bounds and all those things that essentially tell us how it converged and how fast it converged. But these are all details. Okay. Which I don't care. I want you to understand why it goes there. If you really want to quantify the size of these tails, you can. But eventually, this is just going to shrink to a distribution which is a delta function in the limit. But before it's a delta function, I can tell you that for every epsilon, most of the mass is going to lie there. That's all it is. Now, why is this so important? Because now it tells us that the entropy is actually measuring the probability. 2 to the minus entropy is the probability of one sequence, and 2 to the entropy is the size of typical sequence. So now I can start counting things in a very profound way. So the next step is really to use this for what we call data compression. Okay, so now we're getting into the real heart of information theory. So the first application of this is what we call data compression. And data compression is one of the two branches of Shannon's theory. How do you represent data in a very short way? And the other one is how do you correct noise errors in channels. But these two branches of these two problems are intimately related. They're somehow dual to each other in a funny way, which we'll see later on, not today. But I already can use the typicality argument to give you an argument of, so let's say that I have sequences, long sequences, I don't know, books, long sequences of characters, of texts, okay? And I'm telling you, okay, all the long books are typical. So the probability of seeing a book which has a long list of X's in it, it's actually not that small, but but a long list of A's or B's, this is a non-typical book. Okay, so the same as the probability of seeing, let's say, a sequence of coin flips which looks like this. Okay, so this is the probability of this sequence. Let's say I'm talking about even coin, and this is size n. So the probability is just like 1 over 2 to the n. Okay? And it's the same as any other sequence of size n for equal coin. It's the same as the 1, 1, 1, 1, 1 or the 0, 0, 0. But still I'm telling you that these particular sequences are not typical. 1, 1, 1, 1 is not a typical sequence. So let's just make it a little slightly more interesting. Let's say that it has p and 1 minus p, or let's call it theta. Theta and 1 minus theta for 0 and 1. Okay. So then what is the probability of a particular sequence? But then you all know it has the probability of size n of having m1s in a sequence is what? Is n over m, theta to the m, 1 minus theta to the n minus m. Okay? Now, this is Bernoulli. Now, what are going to be the typical sequences here? So you see the probability of the sequence depends only on the number of 1 and the number of zeros. It's all the same. But somehow they have different factors here. So those binomial factors are going to say that most of the sequences are going to be where? If n is large enough. So you know how the binomial factors look, no? I hope you know. What are these numbers? Okay, so they look like the Pascal triangle, yeah. And so on. You know how to calculate this? Each number is just the sum of the two above it, the two parents. And these are precisely how the binomial coefficients behave. And surprisingly enough, those numbers are going to concentrate somewhere in the middle. Okay? So when you look large enough, so n over m, what is n over m? Is n factorial over m factorial, n minus m factorial. And these numbers are going to concentrate